I am, as Konstantin Szaniawski said, I am PhD student at Faculty of Mathematics and Information Sciences of Warsaw University of Technology, and also a specialist at mathematician at National Cybersecurity Center. It's a Polish government institution whose tasks are investigating cybersecurity, cryptography, and IT connected with cybersecurity in general. As you see on the slide, you can see logos of all places, I mean. But maybe you want to ask me or yourself or somebody else a question: why should we consider lattice-based cryptography instead of other classes of post-quantum cryptography? Are other crypto systems worse? In fact, I don't know are other types worse, but I know that lattices have very interesting mathematical background. The other reason why we should consider it is that at July 22nd this year, the finalists of post-quantum cryptography competition were announced. Dr. Chen's talked about them before me, so you can ask her about details, and she said you details. I will not tell you today. And 3 out of 4 finalists in the category of public key encryption and key establishment algorithms were lattice-based. Okay, therefore maybe it's a good idea to investigate lattices instead of other post-quantum cryptography classes. As you see, the finalists were Crystal Kyber and True Saber. These 3 were lattice-based, and the only non-lattice-based finalist was classical Michaelis. Let's start from the definition of the lattice. It's important because there is a lot of more or less general definition of lattices. For example, some people will say that each finitely generated module embedding into real vector space is a lattice, but I will use some less general and more common in cryptography definition presented on the slide. If n and m are positive integers and b1 to bm are linearly independent vectors from the space Rn, then the lattice generated by b1 to bm is the additive subgroup generated by these vectors. Okay. To truly understand problems, lattice-based problems, which were useful for constructing lattice-based cryptosystems, we need to have some norm on the space Rn, and also we need some distance inducted by this norm. In general, we can take any norm, but the most common norms used in cryptography are Euclidean norm and maximum norm. During my presentation, I will at first present you 4 lattice-based problems, and after that 3 to 4 public key encryption schemes. It depends how you look at schemes. And the first 2 problems I will talk today about are shortest vector problem and closest vector problem. They both are similar and equivalent. And these 2 problems had a great impact on lattice-based cryptography before 2005. They are also known to be NP-hard. The shortest vector problem in the lattice L concerned about finding a non-zero vector in L with the smallest norm among all vectors. Among all vectors of L, of lattice L, And the closest vector problem definition is similar. We have some point t from the lattice, and we look for some point of the lattice, which is not equal to this point t we have, which distance to the t is minimal. Is the smallest. Minimal is better to say. Okay. We can also consider a little bit simpler decision variant of shortest vector problem and crossover vector problem too. And these two decision variants concern about answering the question, is there any point of the lattice? Okay, is there any point of the lattice L in the ball with a given radius r? This ball has a center in the lattice point, except of this center. Okay. There are also possible to consider approximate versions of SVP and CVP. They differ from the regular versions in that they give ourselves an error we can make. For example, in approximate CVP, we want to find a really small, but not necessarily the smallest non-zero vector in the lattice. Let gamma be a real greater than 1, for example. Then the purpose of approximate SVP is to find a non-zero vector y such that it differs from the smallest one maximally gamma times. And approximate CVP is defined in the similar way. The other interesting lattice-based problem, and in my opinion, and I think in opinion of a lot of people, the most interesting in cryptography lattice-based problem is learning with errors. It was formulated by Regev in 2005, but some similar problems were considered earlier, even in 1988. So maybe it's not easy to say who is the author of this problem, but Regev formulated it as we know it now in 2005. So if A is a real matrix of some dimensions n and m, and B is a real vector, and he is a distribution over Rm, then to solve the learning with errors problem, means to find an integer vector s such that the equation I present on the slide holds, where E is some unknown vector chosen according to distribution He. Of course, you can consider also decision variants of LWE problem. And usually in cryptography, a lot of these matrices, these vectors has integers values. For example, it is quite common for the distribution He to take integer values. If you want some more information about learning with errors problem, I put some papers about this problem on the bottom on the slide. You can look there if you're interested. The learning with rounding problem is a special case of learning with errors problem. And according to my knowledge, it was formulated and used in the cryptography in 2012 for the first time. But as with the rounding with errors, similar problems, similar ideas were considered earlier in 1988, for example. This problem were connected with machine learning. Maybe it's good to say it now. And if A is a real matrix and B is some integer vector, as on the slide, then the learning with rounding problem consists of finding an integer vector s such that the result of rounding, the result of multiplying matrix A by vector s is equivalent to B modulo sum P. Yes, and there is some work about learning with rounding problems. In the next part of the presentation, I will consider some examples of lattice-based public key encryption schemes. And the first crypto system I will analyze today is Entru, proposed in 1996. And this crypto system is based on SVP problem and is the oldest example I will talk today about. Of course, there are some oldest lattice-based crypto systems, but I will not talk about today. I chose some most interesting for me crypto system to show you, and it is one of them. So if NP and Q are integers, such on the slide, so Q is greater than P, much greater than P, and P and Q are coprime. It define also the ring R as on the slide, and for simplicity of the notation, let star denote the binary operation of multiplying in R. Here's the definition of this multiplying. If you are interested, we can write it here. This ring is quite easy to count. The parameters of the Entru crypto system are NP and Q, I have mentioned before. And the private key of Entru crypto system is a pair of polynomials f and g from R, such that one of this polynomial g is totally random, and another one, f, is invertible modulo p and invertible modulo q. By that, I mean that there exists some fp and fq in R, such that fp star f is equivalent modulo p to 1, and fq star f is equivalent to 1 modulo q. Maybe it is by getting modulo p the polynomial, I mean getting all of its coefficients modulo p. Yeah. To be concrete. Okay, there's nothing more. And the public key of the Entru is h equal to fq star g modulo q. So it's done. Okay, the message of Entru crypto system is an integer polynomial, integer polynomial with coefficients less than p. To encrypt the message m, at first choose some random polynomial r from the ring R, and the ciphertext of Entru is equivalent to sum of m plus pr star h modulo q. And if you want to decrypt the ciphertext C, we need to find A equal to f star C equivalent to f star C modulo q, and the message should be equal fp star A should be equivalent to fp star A modulo p. And I am not, I'm sure a lot of you have seen that, but maybe some of you didn't. So I think it's a good idea to ask myself a question: why Entru works? What is it possible? Is it if we have a message and we at first encrypt this and after that we decrypt this message, should we get M? and does it hold in entry? Because if you look at that definition of encryption, it is maybe hidden. It is not clear why this crypto system works. And to ensure you that it does, at first note that A I have presented on the previous slide can be presented in the form PR star G plus F star M modulo Q, yeah? It can be because FQ star F is equivalent to 1 modulo Q, and of course the operation of multiplying in ring is associative, commutative, and distributive over addition. Yeah, so we can get this A in this form. Moreover, if P and Q are chosen properly, by that I mean that Q is much bigger than P, then the absolute value of A, the coefficients of absolute value of A should be less than Q. Therefore, we can omit the modulo Q operation of the end of A. And if we do that, the result of decryption of the ciphertext should be equivalent to modulo P to M, because FP star F is equivalent to 1 modulo P, and PR is equivalent to 0 modulo P. Therefore, entry works. Now we will consider some LWE and LWR-based cryptosystems. And to understand them well, I think I should present at first the general cryptosystem proposed by Regev in his works. And understanding this general cryptosystem, in my opinion, can be helpful in understanding more concrete examples. As you see on the slide, the cryptosystem has a lot of parameters, and the most interesting among all of them is some distribution over the space of integers. To make the cryptosystem work, the distribution should be chosen properly. More example about how we can choose he and other parameters you can find in Regev works or other literature. To simplify the notation, let us define the rounding function f from ZTL into ZTQ, defined as on the slide. And as you can see, each coefficient of an input vector is multiplied by Q, divided by L, and rounded to the nearest integer. Of course, such function f is not invertible, but we will define f minus 1 as the closest candidate to being the invert function. And we will define it as on the slide, similarly to f. Okay, the private key of this general one cryptosystem is a matrix S, and some matrix S with integer elements, and public key is pair of matrices where A is random matrix and P is a sum of P is equal to AS plus E, where E is chosen according to distribution E and is unknown. The message of this general one cryptosystem is some vector of integers. Okay. To encrypt the message M, at first choose a random integer vector I with elements between -r and r. The ciphertext is a pair of vectors u and c, where u is equal to transposition of a multiplied by small a, and C is transposition of P multiplied by small a plus rounded message M. During the decryption process, the message M should be equal C minus transposition of S multiplied by U, and all of it should be under the rounding function f minus 1. And of course, it is not hard to see that this crypto system can't sometimes work, may sometimes not work, may sometimes not work. And in fact, it may not work for any instances of this crypto system, for any parameters. And for some chosen parameters, it holds the condition M equal decryption of encryption of M holds really rarely. And in good LWE crypto system, this probability that the message is equal to decryption of encryption of message should be really high. And how you can choose parameters of this crypto system, you can find it in regEFWorks, but for any parameters, there can be some messages and some situations that the decryption process does not pass. This M equal to decryption of encryption of M does not hold. This will go. And the next two examples of crypto systems show how to build crypto system with good probabilities of non-errors or less probabilities of errors in decryption. And the first of them is, of course, Crystal Kyber, the one of the finalists in PQC competition. And this crypto system is quite young. It was created in 2018 and is based on LWE problem. In fact, it's based on a special case of LWE problem called module learning with errors. But I will not talk today about the differences. And if you are interested, what are the differences between MWE and MLWE, you can find it in the work I put below. And let's start from the definition. So define two rings R and RQS on the slide, and let us consider the two functions, com and decom of compression and decompression. These two functions are generalizations of functions f and f minus 1 I have defined before. And here, by rounding a polynomial, I mean rounding each of its coefficients to the nearest integer. The Crystal Kyber crypto system have 5 parameters, 5 integer parameters, and one binomial distribution He. The binomial distributions are quite common in lattice-based cryptography. The private key of this crypto system is also similarly like in general one, some vector. Here it's a private key. It's some matrix S, which coefficient generating according to the distribution He. And the public key, similarly like in general one, is a pair of matrices. One is chosen randomly, and the other one, P, is equal to compression of AS plus E, where E is each coefficient of E is chosen according to distribution He. Okay, the message of Crystal Kyber is some polynomial with coefficients equal 0 of 1. Therefore, we can interpret this message as a binary vector. And I think it's comfortable for us, because encrypting binary vectors is good, and we think good to have to be able to do that. And to encrypt the message M, at first choose randomly k-element vectors R and E1 according to he, and some element E2 also according to distribution he. The ciphertext of Kyber is a pair U and V, defined as on the slide, and some differences between this ciphertext and ciphertext in general one LWE problem comes from two reasons. One of them is making the keys smaller, and another one is trying to make the probability of errors as low as possible. And that's why we have some differences here, but they are not important in how it works. Similarly, the output of Crystal Kyber is also similar to the output of General 1 crypto system. The last crypto system I will mention today is Saber. This crypto system is based on LWR problem, and is the last lattice-based finalist of PQC encryption schemes I haven't taught yet. This crypto system uses R and RQ, rings R and RQ as Kyber, and also uses composition and compression and decompression functions from Kyber 2. They have been. This crypto system also comes from 2018, so they are from the same period of time. The parameters of Saber are 3 positive integers, 1 binomial distribution, similarly like in Kyber, but what is interesting, also some vector, some chosen vector, constant vector h over aq, and an element h1 also from rq. The private key and the public key of Saber are similar to this of Kyber, but there is some difference, and the difference is in the public key, in the definition of mass of P, because we there do not use any error message, but we use some constant. We use constant h, and that's why we generate the public key without any errors. Okay. Similarly, similarly to Kyber, the message of Saber is some polynomial with coefficients equal 0 of 1, so we can interpret it as a binary vector. And encryption and decryption are also similar to the General 1 crypto system. I will do not talk much about differences here between Saber and Crystal Kyber, but you can see that in fact we do not use. You can see here that the errors in Saber are deterministic, not as in the Kyber, in the Crystal Kyber, where the errors were random, were not deterministic. And maybe we need some summary of the topic of lattice-based cryptography. I wanted to show you that the lattice-based cryptography gives us important topic in post-quantum cryptography, and maybe it is not necessarily the most important, but in my opinion, lattice-based cryptography is an important part of future standards in cryptography and also in cybersecurity. As you see on the slide, I put some literature about lattice-based cryptography. If you're interested, you can look there for some knowledge, and thank you for your attention.